Okay. So, let us look at these factors which actually causes this design of the axial flow compressor. We have looked at how the different parametric basic design parameters like rotational speed, blade and all these, and what the kind of forces they are exposed to. So, we are looking at now the tip Mach number. So, this I said that because this is another important parameter, because the maximum Mach number in the axial flow compressor occurs at the blade tip of the rotor inlet on the first stage. So, this is essentially maximum at blade tip of the rotor inlet of the first stage. Okay. So, this is due to the maximum value of the relative speed W1 and the maximum static temperature of the sonic inlet. So, the for the first stage the axial velocity is equal to the inlet absolute velocity and has a constant value along the annulus. So, the corresponding maximum Mach number which we can estimate Mach tip is m1 max, which is W1 max by A, which is V1 square plus U tip square by gamma r T1, which one can write V1 square plus U tip square by gamma r T01 minus V1 square by 2 Cp. So, m1 max would be U tip V1 by U tip square plus 1 gamma r T naught minus V1 square by 2 Cp. Okay. So, from this particular equation for a specified tip Mach number and rotational speed, the axial velocity at the inlet can be determined. Now, for a transonic compressor, an acceptable value of tip Mach number would be around 1.3, while the fan in turbofan engines much higher Mach number is expected and allowed. So, which would be typically 1.5 to 1.7. So, the challenging design is to increase the rotational speed u and keep the tip Mach number with the acceptable limits. So, this can be achieved by inlet guide vanes. So, we can see how, I mean already we have looked at that, but again just to reiterate the fact by showing some. So, the velocity triangle would be like this. So, this is V1 U, this is W1 and this is Vz, this is A. Now, that V0 which goes in. So, these are the blades here. So, when it comes out, that comes out, this is U, this is W1. So, that is Vz1 and this is U, V1. Then again, so this goes back. So, that is how the U also. So, this is two different scenario. This section is A. So, this is a situation where rotor, this is rotor without IGV, inlet guide vane. So, this is how it happens, and this is a case with rotor. This is rotor with IGB. So, with the presence of inlet guide vane, you can actually increase the speed, but at the blade speed, but at the same time the tip Mach number can be kept within the acceptable limit. So, if we also add a swell component to this V1 here, then this can reduces the relative speed of W1. Now, one has to note that the passage of the inlet guide vanes are nozzles to increase the absolute speed of V1, which is greater than V0, thus keep a constant axial velocity of Vz. Now, the maximum tip Mach number would be W1 max by gamma r T1. So, now one can see this is u minus V1 sin alpha 1 plus V1 cos alpha 1 square by gamma r T naught 1 minus V1 square by 2 Cp, where alpha 1 is the angle between the absolute velocity and the axial direction. Thus, the maximum relative Mach number can be written as u square plus V1 square minus 2 u V1 sin alpha 1 by gamma r T naught 1 minus V1 square by 2 Cp. Okay. So, this is what it happens. Now, the other condition is the fluid deflection. Okay. So, that means beta 2 minus beta 1. So, this is the difference between the outlet and inlet angles. This is for rotor, and for stator it could be alpha 3 minus alpha 2. So, excessive deflection in the flow angle, which means a high rate of diffusion, will lead to blade stall. So, high deflection leads to stall. So, to maximize the specific work and the difference between the flow angles in rotor must attain a maximum allowable value. So, if the inlet relative velocity maintains a constant angle beta 1, then the outlet velocity will control stall and in other condition. So, one can look at the situations where, let us say, when you have a passage of cascade, you can look at how things looks like this. So, you have essentially blade like this. So, this is the pressure side, then this is the suction side, and typically this is the quad and this is the pitch. So, this is quad percentage. So, this is 100%, 0. So, that is V max, this is suction surface, this is V2, this is mean velocity in passage, and this is pressure surface. So, what happens that a constant axial velocity is assumed, then the relative angle is measure of a magnitude of the relative velocities W1 and W2. So, the criteria which is called the diffusion factor or the DF. So, this was developed by NACA, which can be adopted here, and another So, this can be defined, the diffusion factor. So, typical diffusion factor is V max minus V 2 by V 1, which is 1 minus V 2 by V 1 plus delta V theta by 2 sigma V 1, where sigma is C by S, pitch is S, chord by C. So, a more precise expression one can write in the mean radius. So, that would be written at 1 plus V 2 by V 1 plus delta R V theta by 2 sigma R V 1. Now, values of dF in excess of 0.6 are throughout to indicate blade stall, and a value of 0.45 might be taken typical design choice. So, this diffusion factor is important, because if you have too much of dF, that means this can lead to high deflection, could lead to the stall. So, for both rotor and stator, it can be combinedly expressed as 1 minus W 2 by W r plus W theta 2 minus W theta 1 divided by 2 sigma r W 1. So, this is rotor, and the stator, it could be 1 minus V 3 by V 1 plus V theta 3 minus V theta 2 divided by 2 sigma S V 2. So, these are two diffusion factor for I mean the way it is defined for the rotor and stator, and that can be used. Okay. Now, these are the some of the discussion on the basic design parameter. Now, if we look at how we go about the basic design procedure, now or rather general. So, we can quickly look upon that thing, the general design procedure. So, already we have discussed the disadvantage of the free vortex method, and now the design is based on arbitrarily chosen radial distribution any two blades, which is essentially the radial equilibrium theory. So, that is radial equilibrium theory, okay, or which is called the vortex energy equation. And so, what we can look at, so the designer usually prescribes the wheel velocity somewhere between a force vortex and the free vortex, and according to the relation. So, the relations like if V theta 1 is A r n minus B by r, or V theta 2 equals to A r n plus B by r. So, r is r by r m, which is u by u me. Now, value of A is determined from the degree of reactions, where psi is 1 minus V theta 1 plus V theta 2 by 2 u. At the mean radius, psi m would be 1 minus V theta 1 m plus V theta 2 m by 2 u m. Now, substitute the values of wheel velocities, then these tangential velocities or component. So, what we get, psi m 1 minus A r m to the power m n plus B by r m plus A r m to the power n minus B by r m. So, divided by 2 u m. So, r m is 1, then this would be 1 minus A by u m, and A is u m 1 minus Im. The constant B, which will be calculated for the constant condition of constant specific work, which is delta H naught, which is constant, that is H naught 2 minus H naught 1. So, Ws is delta H naught, which is u v theta 2 minus v theta 1. So, what we can write UMR A r to the power n plus b by r minus A r to the power n minus b by r. So, this leads to 2 b u m delta H naught by 2 u m. So, once you have these values of A and B, so these are, one can see these values are independent of R, and this can be used. Now, the total enthalpy upstream of the stage H naught 1 is assumed to be constant and independent of R, and since work or the specific work is H naught 2 minus H 1 work, which is also assumed to be constant, the downstream enthalpy H naught 2 is also constant. So, if this is constant and this was at the ahead of it assumed to be constant, so this becomes also constant. Now, this actually the already we have seen the radial equilibrium theory, which we have obtained that. So, which we have already got d h naught by d r is 0, and that is what we have already got here. So, if you recall that d h naught by d r 0, so from the radial equilibrium theory, so we can put that thing back and the similar thing and write the Vz in terms of R and all this. So, then we can find out all this. So, Vz by dVz by dr plus b theta by dv theta by dr plus b theta by r 0. So, it can be integrated between station 1 and 2 and mean radius r. So, where r m is 1, b theta 1 m is a minus b, b theta 2 m is a plus b. So, the resulting values of axial velocities at radius in station 1 and 2 can be calculated. Okay. And there are a big, so different ways one can do that. So, for example, let us say we put v theta 1 equals to a r to the power n my b by r. Okay. If it is there, then a would be u m 1 minus this. If v theta 2 is a r to the power n minus plus b by r, then we get b equals to C p delta T naught s by 2 u m, or now we can have different kind of bleeding and different values of. So, this is what we have, this is bleeding, Vz, then we get degrees of reaction b theta. So, these are different. So, one case it could be free vortex where n equals to -1, then V z 1 equals to V z 1 m, V z 2 equals to V z 2 m, V, and this would be, so, and V z 1 m is V z 2 m. So, degrees of reaction would be 1 minus A by u m r square, 1 minus xi m by r square, and V theta 1 is A minus B by r, V theta 2 A plus B by r. You can have exponential which is n 0, then V z 1 square minus V z 1 square m is minus 2 A square ln r plus A b by r minus A b. Similarly, V z 2 square minus V z 2 m square equals to minus 2 A square ln r minus A b by r plus A b. So, V z 1 m equals to V z 2 m, and V z 2 square minus V z 1 square equals to 4 A b 1 by r minus 1. Degrees of reaction would be 1 plus A by u m minus 2 A by u m r, and this would be 1 plus 1 minus 2 by r 1 minus xi m, and V theta 1 is A minus B by r, V theta 2 A plus B by r. Or you could have first power, that is n equals to 1. Then this pattern would be V z 1 square minus V z 1 m square equals to minus 2 A square r square minus 1 minus 2 A b ln r, V z 2 square minus z 2 m square equals to minus 2 A square plus 2 A b ln r, V z 2 square minus V z 1 square equals to minus 8 A b ln r, V z 1 m equals to V z 2 m, and degrees of reaction will be 1 plus 2 A ln r minus A by u m by u m. This is 1 plus 2 ln r minus 1 minus I m, and V theta 1 would be A r minus B by r, V theta 2 is A r plus B by r. So, you can see when you consider the different design, so you have to assume some of this design procedure and then follow the basic Gaoni equations or laws to find out these different components. So, this comes all in the design procedure. Now, one can think about some conceptual design, how to get it for axial compressor. So, typically the compressors are designed by indirect method. So, the first one defines the flow path, that means casing and half radius, and decides the thermodynamics, aerodynamics forces, and then the flow path. And iterative analysis is conducted with the continuity, momentum and energy equation. For such conceptual designs, there are different stages, like you can have quasi 3D analysis, or you could have experimental analysis or testing of the blades and things like that. Now, or you have of design performance analysis. So, the first step for quasi 3D starts by 2D analysis, which is axial, tangential and then extend, and this extend the define the flow parameters. So, provides a quasi 3D analysis. Details of such step one can have, you can have a choice of compressor data like rotational speed, axial velocity, and then the annulus or rather dimension or dimension of the annulus, and then you can define the number of stages or determine the number of stages. So, here you have to assume the efficiency, then you can calculate all the angles at stages. So, that mean section. So, once you calculate all the angles at the stages of the mean section, then you can find out the determine the variation of the air angles from rotor to tube by different blading like free vortex or exponential or power, like that. So, this is what one can do or think about the analysis which requires the 3D analysis. So, 3D quasi analysis starts with the 2D analysis, where you assume some of this speed, axial velocity, dimensions, and then determine some of these parameter. Or in a other way, if somebody does experimental analysis of the blades, blading, you can choose the blade from the experimentally cascade data. So, then you can check efficiency which is compared to the assumed cascade data, and then finally look at the other effects like compressibility and such parameters, and then you go for the off design performance analysis. So, essentially this kind of conceptual design, if you look at it, the in the compressor design, so you go in 3 different stages or steps. Step 1, you have quasi 3D analysis. Step 2, you have experimental analysis, and finally the off design performance analysis. So, in a quasi 3D analysis, it starts with some 2D analysis where you assume certain parameters like speed, axial velocity, dimensions and all these, then calculate some of the other parameters, and then go to the experimental analysis where assuming those blade parameters, you do the testing done and check the efficiencies, the compressibility effects, such things, and finally the off design performance analysis. So, this is how the conceptual design is done, and we will look at some of these system in slightly in details in the subsequent lectures.